On the Origin of Time, Thomas Hertog invites readers to embark on a profound exploration of the nature of the universe, the origins of time, and the deep mysteries that continue to challenge our understanding of cosmology. Hertog, a distinguished physicist and former collaborator of the late Stephen Hawking, builds on the groundbreaking ideas that the two developed together in their quest to unravel the enigma of the universe's beginning. This book not only reflects Hertog's deep engagement with Hawking's ideas, but also pushes the boundaries of traditional physics, venturing into new and uncharted territories of thought. The title, On the Origin of Time, is a nod to Charles Darwin's On the Origin of Species, suggesting that just as Darwin's work transformed our understanding of biological life, this book aims to revolutionize how we think about the universe's inception and the nature of time itself. Hertog argues that to fully grasp the origins of the universe, we must rethink many long-held assumptions about time, space, and the physical laws that govern our reality. Central to this inquiry is the realization that the universe is far more complex and interconnected than previously imagined. Hertog takes readers beyond the traditional boundaries of physics, cosmology, and the philosophy of science, inviting them to reconsider the relationship between the observer and the cosmos. His work is not just a continuation of Hawking's legacy, but an expansion of it, challenging the very foundation of what we know and leading us toward a deeper understanding of time's origin and role in shaping the universe. Hertog's reflections are both scientific and philosophical, making this book as much about the human pursuit of knowledge as it is about the cosmos itself. Part 1. The Limits of Physics. In this first part of the book, Hertog sets the stage for his exploration of time and the universe by addressing the limitations of current physical theories. Despite the incredible advances made in physics over the past few centuries, from Newton's laws of motion to Einstein's theory of relativity, Hertog argues that we are still far from having a complete understanding of the universe. He presents a compelling case for why our traditional models of physics, while incredibly powerful, are insufficient when it comes to explaining the deepest mysteries of the cosmos. Chapter 1. The Edge of Knowledge. The journey begins with Hertog highlighting the boundaries of our current scientific knowledge. Classical physics, grounded in the deterministic laws established by Isaac Newton, offers an incredibly accurate description of how objects move and interact in the universe. Newton's laws allowed us to predict planetary motion, describe the forces at play in everyday life, and even send humans to the moon. However, as Hertog explains, when it comes to the most extreme environments, such as the very beginning of the universe or the interior of black holes, these classical laws no longer apply. Hertog transitions to a discussion of Einstein's theory of general relativity, which brought a revolutionary new understanding of gravity and the fabric of spacetime. With general relativity, Einstein showed that massive objects like stars and planets warp the space around them, bending light and influencing the movement of other objects. This theory has been validated by countless experiments, including the recent detection of gravitational waves. Yet, as powerful as general relativity is, it too faces limitations, particularly when combined with quantum mechanics. Quantum mechanics, developed in the early 20th century, governs the behavior of particles on the smallest scales, such as atoms and subatomic particles. It is a theory of probabilities and uncertainties, contrasting sharply with the deterministic world of Newtonian physics. While both general relativity and quantum mechanics are incredibly successful in their respective domains, they are fundamentally incompatible. Hertog points out that physicists have long struggled to reconcile these two pillars of modern science. This tension becomes especially pronounced when we attempt to understand the very beginning of the universe, where both quantum effects and gravitational forces are at play. At the heart of the problem is the fact that the laws of physics, as we currently understand them, break down at certain points, most notably at the singularity of a black hole and the very moment of the Big Bang. At these extremes, space and time become so distorted that our current mathematical tools fail. Hertog emphasizes that this is not just a technical problem, but a profound philosophical one. It suggests that our traditional concepts of time, space, and causality may not apply in these extreme situations. This realization sets the stage for the deeper exploration that follows in subsequent chapters. Chapter 2: A Universe from Nothing. In this chapter, Hertog dives into one of the most perplexing questions in cosmology. How did the universe come into existence? The traditional view of the Big Bang suggests that the universe began as a singularity, a point of infinite density and temperature, which then expanded into the cosmos we observe today. However, Hertog challenges this classical view by drawing on the revolutionary ideas he developed alongside Stephen Hawking, particularly the no-boundary proposal. The no-boundary proposal, first introduced by Hawking and Hertog, posits that the universe did not have a singular, well-defined beginning. Instead, it suggests that time itself may have had a soft origin, where the classical concepts of space and time break down in the extreme conditions of the early universe. According to this model, the universe didn't emerge from a singularity, but rather from a smooth, quantum state in which time and space were not clearly distinguishable. This is a radical departure from the traditional Big Bang model, which assumes a sharp beginning at a specific point in time. Hertog explains that in this view, the universe could have emerged from nothing, not in the sense of an absolute void, but in a quantum mechanical sense, where the laws of physics allow for the spontaneous creation of the universe from a quantum fluctuation. This idea is deeply counterintuitive, but Hertog walks readers through the scientific reasoning behind it, emphasizing that at the quantum level, the distinction between something and nothing becomes blurred. Moreover, Hertog discusses how the no-boundary proposal ties into the concept of imaginary time, an idea first proposed by Hawking. In this framework, time behaves more like space in the early universe, allowing for a seamless transition from a timeless quantum state to the classical spacetime we experience today. The implications of this are profound. It suggests that time itself is a product of the universe's creation, emerging gradually rather than appearing instantaneously at the moment of the Big Bang. This chapter challenges our most fundamental assumptions about the nature of time and the universe's beginning. Hertog urges readers to reconsider the notion of a singular point of origin and instead embrace the idea that time, space, and matter arose out of the quantum foam, governed by the probabilistic rules of quantum mechanics. The universe, in this view, is not the result of a deterministic process, but rather a quantum event, a profound shift in how we think about the cosmos and its origins. Chapter 3: The End of Predictability. Hertog continues his exploration of the limits of classical physics by tackling the issue of predictability. For centuries, scientists believed in a deterministic universe, where knowing the laws of physics and the initial conditions of a system would allow us to predict its future with complete certainty. This view was encapsulated by the famous metaphor of Laplace's demon, a hypothetical intellect that, knowing the positions and velocities of every particle in the universe, could predict the entire future of the cosmos. However, the advent of quantum mechanics shattered this deterministic worldview. Hertog explains that in the quantum realm, uncertainty reigns supreme. The famous Heisenberg uncertainty principle tells us that it is impossible to know both the position and momentum of a particle with absolute precision. This fundamental uncertainty leads to a universe that is inherently unpredictable at the smallest scales. Events at the quantum level are governed by probabilities, not certainties, meaning that even with complete knowledge of the initial conditions, we can only make probabilistic predictions about the future. This unpredictability extends to the formation of the universe itself. Hertog argues that the early universe was not a simple, deterministic system, but rather a complex and chaotic environment where quantum fluctuations played a crucial role. These fluctuations may have determined the structure of the universe, including the formation of galaxies, stars, and planets. In other words, the universe we observe today may be just one of many possible outcomes shaped by random quantum events. Hertog also touches on the idea of the multiverse, a controversial but intriguing concept in modern cosmology. According to some interpretations of quantum mechanics, our universe may be just one of many universes, each with its own set of physical laws and initial conditions. If this is true, the universe we inhabit is just one possible outcome in a vast, unpredictable cosmic landscape. This idea further challenges the notion that the universe follows a single predetermined path. In this chapter, Hertog pushes readers to reconsider the very nature of reality. The universe is not a clockwork machine that follows a fixed trajectory, but a dynamic, evolving system shaped by the interplay of quantum uncertainty and cosmic forces. Predictability, once a cornerstone of classical physics, has given way to a new understanding of the universe as a place where randomness and probability play central roles. Part 2, The Quantum Universe. In Part 2 of On the Origin of Time, Thomas Hertog takes readers deeper into the mysterious world of quantum mechanics, offering a new lens through which to view the origins and evolution of the universe. As he builds upon the groundwork laid in Part 1, Hertog challenges classical notions of reality, pushing the boundaries of what we understand about the fabric of the cosmos. This section delves into the quantum nature of reality, exploring how the universe might have emerged not from a deterministic event, but from a fundamentally uncertain and fluctuating quantum state. Hertog introduces groundbreaking ideas that bridge quantum mechanics with cosmology, weaving complex mathematical theories with philosophical insights. In doing so, he opens up a new realm of possibilities, suggesting that the universe itself and time as we know it might be better understood through the lens of quantum physics rather than classical models. This shift has profound implications for our understanding of the universe's birth, its structure, and the very nature of reality. Chapter 4: Quantum Creation. Hertog begins this chapter by tackling one of the most perplexing questions in modern cosmology. How did the universe begin? He turns to the principles of quantum mechanics to offer a radical new perspective, arguing that the universe may not have had a traditional beginning in the sense we typically imagine. Instead, it could have emerged from a quantum process where the creation of space, time, and matter was a probabilistic event driven by quantum fluctuations. At the heart of this idea is the concept of quantum creation, a theory that suggests that at the smallest scales, particles and energy constantly fluctuate, popping in and out of existence. These fluctuations, governed by the laws of quantum mechanics, are not deterministic, but instead governed by probabilities. Hertog explains how this same mechanism might apply on a cosmic scale. In this view, the universe itself could have originated from a quantum fluctuation in a pre-existing quantum vacuum, where neither time nor space existed in any traditional sense. Hertog breaks down the complex mathematics that support this idea, offering a detailed exploration of how quantum fields interact at the smallest scales. He delves into the concept of the quantum foam, a turbulent, chaotic state where the classical laws of physics, such as those that govern cause and effect, no longer apply. In this foam-like state, virtual particles constantly appear and disappear, and it is from this highly unstable quantum environment that the universe may have emerged. One of the key insights of this chapter is the idea that time itself may have been born from this quantum process. In the quantum world, time does not behave the way we experience it in our everyday lives. Instead, time could be understood as a product of the universe's emergence from quantum uncertainty. Before the universe hardened into the classical reality we observe today, time might have been fluid or even non-existent in the way we traditionally conceive of it. Hertog suggests that this quantum origin of time fundamentally changes how we think about the Big Bang. It was not a singular, well-defined moment of creation, but rather a transition from a quantum to a classical state. Hertog builds on the no-boundary proposal he developed with Stephen Hawking, explaining how their theory suggests that time could have had a smooth, rather than abrupt, beginning. Instead of an explosive singular event, the universe may have grown out of this quantum uncertainty, transitioning gradually from a formless quantum state into the structured universe we see today. This view challenges the traditional notion of a singular moment of creation and instead proposes a more fluid, emergent process, i.e., in this chapter, Hertog presents quantum creation not just as a speculative theory, but as a plausible alternative to the standard Big Bang model, supported by the latest developments in quantum cosmology. He shows how the quantum nature of reality allows for a universe that is fundamentally unpredictable at its core, but one that gives rise to the stable, structured reality we observe on the macroscopic scale. Chapter 5: The Holographic Universe. In this chapter, Hertog explores one of the most mind-bending concepts in modern physics, the idea that the universe might be a hologram. The holographic principle, first proposed by physicists Gerard 't Hooft and Leonard Susskind, is a radical theory that suggests that all the information contained within a three-dimensional universe can be encoded on a two-dimensional surface. Hertog explains how this principle has profound implications for our understanding of the universe's structure, particularly when it comes to black holes and the origins of the cosmos. The holographic principle emerged from attempts to reconcile the laws of quantum mechanics with general relativity in the context of black holes. Traditionally, black holes were thought to trap everything, including information, that falls into them. However, physicists realized that this posed a problem for the laws of quantum mechanics, which state that information cannot be lost. To resolve this paradox, the holographic principle was proposed, suggesting that the information contained within a black hole is not lost but rather encoded on its surface, the event horizon. Hertog builds on this idea, suggesting that the entire universe may work in a similar way. He explains how, at the most fundamental level, our three-dimensional reality might be a projection of information encoded on a two-dimensional boundary. This idea is deeply counterintuitive, but it offers a way to resolve some of the paradoxes that arise when trying to unify quantum mechanics and general relativity. One of the most important implications of the holographic principle is that it offers a new way of thinking about space and time. In a holographic universe, the fabric of reality itself is not what it seems. It is a projection of more fundamental, underlying information. Hertog explains how this perspective changes our understanding of the early universe, particularly when it comes to the nature of space and time at the Big Bang. Hertog goes further, applying the holographic principle to cosmology. He suggests that the early universe might have been encoded on a two-dimensional surface, with the three-dimensional universe we observe today emerging from this underlying information. This radical shift in perspective could help explain some of the deepest mysteries of cosmology, including the nature of black holes, the origin of time, and the structure of the universe. This chapter not only explores the theoretical implications of the holographic universe, but also delves into the experimental evidence that supports it. Hertog discusses how recent developments in string theory and quantum gravity suggest that the holographic principle may indeed be a fundamental aspect of reality. He also highlights ongoing research efforts to test the holographic principle, including studies of black holes and gravitational waves. By the end of this chapter, Hertog has thoroughly convinced the reader that the holographic principle is not just a speculative idea, but a serious contender in the quest to understand the deepest mysteries of the universe. The notion that our universe might be a hologram challenges everything we thought we knew about space, time, and reality, opening up new possibilities for understanding the cosmos. Chapter 6: Cosmic Symmetry Breaking. In this pivotal chapter, Hertog turns his attention to one of the most crucial processes in the evolution of the universe: symmetry breaking. At the moment of the Big Bang, the universe is thought to have been in a highly symmetric state, where all the fundamental forces and particles were unified. However, as the universe expanded and cooled, this symmetry broke, leading to the formation of the distinct forces and particles that make up the universe today. Symmetry breaking is a central concept in understanding how the universe evolved from a simple, featureless state into the complex cosmos we observe. Hertog explains that in the early moments after the Big Bang, the universe was governed by a single, unified force. However, as the universe expanded and cooled, this symmetry was broken, causing the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, to emerge as distinct entities. This process is known as cosmic symmetry breaking, and it is responsible for the diversity of particles and forces that make up the universe. At its core, symmetry breaking is a quantum process, driven by the interactions between quantum fields. Hertog delves into the mathematics of symmetry breaking, explaining how the universe transitioned from a high-energy, symmetric state to a lower-energy, broken symmetry state. He also explores the role of the Higgs field, which played a key role in giving particles mass during the symmetry breaking process. One of the most fascinating aspects of this chapter is Hertog's discussion of how symmetry breaking led to the formation of structure in the universe. In the highly symmetric early universe, there were no galaxies, stars, or planets. Everything was uniform and featureless. However, as symmetry broke, small quantum fluctuations in the density of matter were amplified, leading to the formation of galaxies, stars, and eventually planets. Hertog explains how this process of structure formation is a direct consequence of the quantum nature of symmetry breaking. Hertog also touches on the anthropic principle, a controversial idea in cosmology that suggests that certain features of the universe, such as the values of the fundamental constants, are finely tuned to allow for the existence of life. He explains that symmetry breaking is one of the key processes that set the stage for the emergence of life, as it created the conditions necessary for the formation of complex structures. Without symmetry breaking, the universe would have remained in a state of featureless uniformity, with no galaxies, stars, or planets to support life. In the final part of the chapter, Hertog explores how symmetry breaking ties into the broader themes of the book, particularly the nature of time and the quantum origin of the universe. He argues that the process of symmetry breaking is intimately linked to the emergence of time itself. In the highly symmetric early universe, time may have been a fluid or even non-existent concept, but as the universe cooled and symmetry broke, time became a distinct and measurable aspect of reality. This idea ties into Hertog's earlier discussion of the quantum creation of time, offering a deeper understanding of how time and the universe are interconnected. Part 3. The Origin of Time. In Part 3, The Origin of Time, Thomas Hertog brings readers to the heart of the book's most revolutionary idea. Time itself may not be a fundamental aspect of reality, but rather something that emerged from the dynamics of the universe's creation and evolution. This section of the book challenges long-held assumptions about time, suggesting that what we perceive as the linear, forward flow of time, past, present, and future, is not inherent to the universe, but is instead a product of its unfolding processes. Hertog builds on his earlier explorations of quantum cosmology and holographic principles to offer a radically new perspective on the nature of time and how it came into being. He suggests that time did not exist in its familiar form at the beginning of the universe. Instead, it emerged as the universe evolved, cooling and transitioning from its initial quantum state into the more structured reality we observe today. Hertog intertwines ideas from quantum physics, cosmology, and thermodynamics to craft a compelling narrative about how time, as we experience it, is deeply tied to the evolution of the cosmos. Chapter 7. The Emergence of Time. In Chapter 7, The Emergence of Time, Hertog introduces one of the book's most profound and potentially paradigm-shifting ideas. Time, as we know it, may not have existed in the earliest stages of the universe. Rather than being a fixed, unchanging dimension through which events unfold, time itself may have emerged from the primordial quantum state of the universe as it expanded and evolved. Hertog opens the chapter by questioning the conventional view of time as a constant, unchanging flow. He challenges the long-standing assumption in physics that time has always existed in the same form, stretching infinitely into both the past and future. Instead, he proposes that time may have been absent or undefined in the initial moments of the universe's existence. In the extremely high-energy, quantum-dominated state immediately after the Big Bang, Hertog suggests that there may not have been a clear distinction between past, present, and future. The very concept of time as a sequential progression of events might not apply to the earliest phases of the universe. To understand this, Hertog asks readers to think about the nature of time in relation to temperature and energy. He explains that in the immediate aftermath of the Big Bang, the universe was an incredibly hot and dense quantum field with no clear structure. In this state, time might have been smeared out or crystallized, much like how water vapor condenses into liquid and then solidifies into ice as it cools. Just as the molecules in water become more organized as it transitions into a solid state, Hertog argues that time crystallized out of the chaotic quantum state as the universe expanded and cooled. This idea is closely linked to the concept of phase transitions in physics. Hertog explains that just as matter undergoes phase transitions, from gas to liquid to solid, the universe itself may have experienced a kind of phase transition that gave rise to time. This would mean that time, like space, is not a static backdrop against which the universe evolves, but a dynamic, emergent feature that came into existence as the universe cooled and began to organize itself. Hertog delves into the implications of this idea, particularly how it redefines our understanding of the universe's earliest moments. In classical cosmology, time is treated as an absolute, something that has always existed and will always exist. But in quantum cosmology, Hertog suggests that time is better understood as a consequence of the universe's evolution. In the quantum foam state that existed before the universe hardened into its present form, time would have been a fluid, undefined concept. Only as the universe stabilized, with galaxies and stars forming, did time become the structured, linear experience we recognize today. This emergent view of time raises profound questions about causality and the very nature of existence. If time is something that only emerged after the universe cooled, what does that mean for the idea of a before the Big Bang? In classical physics, we are accustomed to thinking of time as something that stretches infinitely into the past, but Hertog challenges this notion. If time itself emerged with the universe, then there may not have been a before, the Big Bang in the traditional sense. Chapter 8. The Evolution of the Cosmos. In Chapter 8, The Evolution of the Cosmos, Hertog builds on the previous discussion of the emergence of time to explore how the universe itself has evolved from its initial quantum state. He argues that the evolution of the cosmos is deeply intertwined with the evolution of time itself. As the universe expanded and cooled, not only did time emerge, but the universe began to develop structure, giving rise to the stars, galaxies, and other cosmic phenomena that we observe today. Hertog begins by discussing how the early universe immediately following the Big Bang was a formless sea of quantum fluctuations. These fluctuations were governed by the strange rules of quantum mechanics, where uncertainty and randomness dominate. In this chaotic environment, the classical laws of physics, such as those that govern gravity and the behavior of matter, did not yet apply. Hertog explains that this quantum uncertainty played a crucial role in shaping the universe's evolution. The universe did not evolve in a predetermined, orderly fashion, but rather through a series of quantum events, each of which influenced the next in unpredictable ways. One of the key concepts Hertog introduces in this chapter is that of quantum entanglement. In the early universe, different parts of the quantum field were entangled with one another, meaning that their fates were inextricably linked. This entanglement played a crucial role in shaping the universe's structure. As the universe expanded and cooled, these quantum entanglements became frozen, creating the seeds of structure that would eventually give rise to galaxies, stars, and planets. Hertog emphasizes that the universe's evolution was not a smooth, continuous process. Instead, it was marked by a series of phase transitions, similar to the way water transitions from vapor to liquid to solid. Each of these transitions represented a major shift in the universe's structure and behavior. For example, the formation of the first atoms marked a key phase transition, as did the formation of stars and galaxies. At each stage, the universe became more structured, more complex, and more stable. Hertog also discusses how the laws of physics themselves may have evolved alongside the universe. In the early moments after the Big Bang, the universe was governed by a single, unified force. As the universe cooled, this force broke into the distinct forces we observe today: gravity, electromagnetism, and the strong and weak nuclear forces. Hertog suggests that this process of symmetry breaking was not just a random event, but an essential part of the universe's evolution. The universe's structure and behavior today are a direct result of these phase transitions and the breaking of symmetries in the early universe. In the latter part of the chapter, Hertog delves into the concept of cosmic inflation, a period of rapid expansion in the universe's early history. Inflation is thought to have smoothed out the universe's initial irregularities, leading to the uniform distribution of matter that we observe today. However, Hertog challenges some of the traditional interpretations of inflation, suggesting that the process may have been driven by quantum fluctuations rather than by a deterministic force. This idea aligns with the broader theme of the chapter. The universe's evolution is fundamentally quantum in nature, shaped by randomness and uncertainty. By the end of the chapter, Hertog has painted a picture of the universe as a dynamic, evolving entity, constantly shaped by the interplay between quantum mechanics and cosmic forces. Time itself, he argues, is a product of this evolution, emerging as the universe became more structured and complex. Chapter 9, The Arrow of Time. In Chapter 9, The Arrow of Time, Hertog tackles one of the most fundamental questions in physics and philosophy. Why does time seem to move in one direction, from the past to the future? This phenomenon, known as the arrow of time, is something we take for granted in our everyday lives, but it poses deep challenges for our understanding of the universe. After all, the fundamental laws of physics do not distinguish between past and future. So why do we experience time as a one-way street? Hertog begins by introducing the concept of entropy, which plays a central role in explaining the arrow of time. Entropy is a measure of disorder in a system, and according to the second law of thermodynamics, the entropy of a closed system will always increase over time. This means that the universe is constantly moving toward a state of greater disorder. For example, if you break a glass, it shatters into many pieces, and those pieces will never spontaneously reassemble themselves. This increase in entropy is what gives time its directionality. As entropy increases, time moves forward. However, Hertog points out that the arrow of time is closely tied to the universe's evolution. In the early universe, right after the Big Bang, the universe was in a highly ordered, low-entropy state. As the universe expanded and evolved, entropy increased, and time began to flow in the direction we experience today. The arrow of time, Hertog argues, is a product of the universe's evolution from this low-entropy state to the higher entropy state we observe now. Hertog explores the implications of this idea for our understanding of time. He suggests that if the universe had started in a state of high entropy, we might not experience time in the same way. In fact, time as we know it might not even exist. The fact that the universe began in a highly ordered state is what allows us to experience the passage of time. This idea ties back to the themes explored in earlier chapters, particularly the notion that time is not an inherent feature of the universe, but something that emerged alongside the universe's evolution. Hertog also delves into the philosophical implications of the arrow of time. If time is a product of the universe's entropy, does that mean time will eventually run out as the universe reaches a state of maximum entropy? Some physicists have suggested that in the far future, when the universe reaches its final state of heat death, where all energy is evenly distributed and no useful work can be done, time may lose its meaning. Hertog discusses this possibility, but he also leaves the question open, acknowledging that our understanding of time is still incomplete. By the end of the chapter, Hertog has provided a comprehensive exploration of the arrow of time, showing how it is deeply tied to the universe's evolution and the laws of thermodynamics. He concludes that the arrow of time is not a fundamental feature of the universe, but rather a consequence of the specific conditions in which the universe began. This insight challenges many of our intuitions about time and leaves readers with much to ponder about the nature of reality. Part 4. A New Perspective on the Universe. In Part 4, A New Perspective on the Universe, Thomas Hertog delves into some of the most radical and mind-expanding concepts in contemporary physics, pushing the boundaries of how we think about reality. Hertog leads the reader through the theory of the multiverse, the intriguing possibility that life plays a pivotal role in the structure of the cosmos, and finally, the suggestion that the universe may have a kind of purpose, not in a religious or deterministic sense, but as part of its fundamental nature. The section offers an awe-inspiring glimpse into the future of cosmology, challenging long-held assumptions and opening up new avenues of inquiry into the very nature of existence. Chapter 10. The Quantum Multiverse. In Chapter 10, The Quantum Multiverse, Hertog explores the tantalizing idea that our universe may be just one of an infinite number of universes, collectively known as the multiverse. This concept arises from the implications of quantum mechanics and the many worlds interpretation, which suggests that every quantum decision point, every possibility at the subatomic level, branches off into a separate universe. Hertog begins by explaining how quantum mechanics introduced profound uncertainty into our understanding of reality. In classical physics, the universe was thought to be deterministic. If you knew the state of a system at one point in time, you could predict its future with certainty. However, the advent of quantum mechanics shattered this notion. Quantum theory tells us that particles do not have definite states until they are observed. Instead, they exist in a superposition of all possible states, and only when an observation is made does one of these possibilities become real. The many worlds interpretation, first proposed by physicist Hugh Everett, takes this uncertainty to its logical extreme. According to this interpretation, when a quantum event occurs, such as a particle taking one path rather than another, the universe splits into two, with one universe representing each possible outcome. Over time, this process leads to a staggering proliferation of parallel universes, each representing a different version of reality. Hertog explains that the implications of this idea are vast. If the multiverse is real, then everything that can possibly happen does happen in some universe. There is a universe where you made every different decision in your life, and another where the laws of physics themselves are entirely different. Some universes may be nearly identical to ours, while others may be radically different, so different in fact that they are unrecognizable to us. He also addresses the criticisms and challenges that the multiverse theory faces. For many physicists, the multiverse is an uncomfortable concept because it seems to defy the principles of scientific falsifiability. How can we test or observe other universes? Hertog, however, argues that the multiverse is a natural consequence of quantum theory, and that while we may not be able to observe these other universes directly, their existence could explain some of the most perplexing features of our own universe. One of the key ideas Hertog explores in this chapter is the role of the multiverse in solving the fine-tuning problem in cosmology. Our universe appears to be finely tuned for the existence of life, with physical constants, such as the strength of gravity or the charge of the electron, set to values that allow stars to form, planets to orbit them, and life to emerge. Some physicists have argued that this fine-tuning is evidence of design or a higher power, while others believe it may simply be a coincidence. Hertog offers a third possibility. If there are countless universes in the multiverse, each with different physical laws and constants, then it's not surprising that one of these universes would have the right conditions for life. We just happen to live in the universe where the conditions are right, because in all the others, life could never have arisen. As the chapter concludes, Hertog leaves readers with a profound question. If the multiverse is real, what does that mean for our understanding of reality? The idea that there are infinite versions of ourselves, living in infinite versions of the universe, challenges our notions of identity, free will, and the nature of existence itself. Chapter 11. Life in a Quantum Universe. Chapter 11, Life in a Quantum Universe, shifts the focus from the structure of the cosmos to the role of life within it. Hertog begins with a question that has fascinated scientists and philosophers for centuries. Is life a mere byproduct of the universe's evolution, or does it play a more fundamental role in shaping the cosmos? Building on the ideas of physicists like John Archibald Wheeler, who proposed the participatory anthropic principle, Hertog suggests that life, and particularly consciousness, may not just be a consequence of the universe's physical laws, but an active participant in its unfolding. Wheeler argued that the act of observation is integral to the way quantum mechanics works. Without an observer, quantum systems remain in a state of superposition, where all possible outcomes coexist. It is the act of observation, that collapses these possibilities into a single reality. Hertog takes this idea further, exploring the possibility that life itself, through the process of observation, plays a crucial role in determining the evolution of the universe. In other words, the universe is not a passive backdrop that life simply happens to inhabit. Rather, life may be a fundamental part of the universe's evolution. He explains that this idea has roots in quantum mechanics, where the role of the observer is central. In the quantum realm, particles do not have definite properties until they are observed. The very act of observation alters the outcome of a quantum event. Hertog asks whether on a cosmic scale life could be playing a similar role. Could it be that the presence of life, and particularly conscious beings, shapes the very structure of the universe? This concept leads Hertog to explore the anthropic principle, the idea that the universe must have the properties necessary for life, because life exists to observe it. There are two versions of the anthropic principle. The weak version, which simply states that we must live in a universe that is compatible with life, because otherwise we wouldn't be here to observe it, and the strong version, which suggests that the universe is in some way designed for life. Hertog navigates between these two versions, proposing a middle ground. While the universe may not be explicitly designed for life, life and the universe are deeply intertwined in a way that goes beyond coincidence. He suggests that the laws of physics and the conditions that allow for life may have co-evolved with life itself. As life became more complex and conscious beings emerged, the universe itself may have evolved in response, becoming more finely tuned for the development of intelligence. This chapter, Hertog emphasizes that this idea, while still on the fringes of mainstream physics, opens up new possibilities for understanding the deep connection between life, consciousness, and the universe. Chapter 12. A Universe with Purpose. In Chapter 12, A Universe with Purpose, Hertog brings his exploration of time, quantum mechanics, and the universe to a thought-provoking conclusion. He suggests that the universe, far from being a purposeless collection of matter and energy, may have a kind of purpose, but not in the traditional sense of the word. Hertog is careful to distinguish his idea of purpose from religious or teleological concepts. He does not argue that the universe was designed by a creator with a specific plan, nor does he suggest that the universe is moving toward a predetermined goal. Instead, he proposes that the universe's purpose can be found in the way it evolves and the role that life plays in that evolution. Hertog begins by reflecting on the key themes of the book: the emergence of time, the unpredictability of the quantum world, and the role of life and consciousness in shaping the cosmos. He suggests that the universe is not a static entity, but a dynamic, evolving system. In this sense, the universe's purpose lies in its continual process of becoming, of evolving into new and more complex forms. He draws on the work of evolutionary biologists and complexity theorists to support his argument. Just as life on Earth evolves through natural selection, with simple organisms giving rise to more complex ones over time, Hertog suggests that the universe itself may be evolving toward greater complexity. This complexity includes not just physical structures like galaxies and stars, but also the emergence of life, consciousness, and intelligence. Hertog proposes that life and the universe are engaged in a kind of feedback loop. The universe gives rise to life, and life, in turn, influences the evolution of the universe. This dynamic relationship, he argues, could be seen as the purpose of the universe, not in the sense that it is moving toward a final goal, but in the sense that its evolution is driven by the interaction between life and the cosmos. Hertog concludes the chapter by offering a hopeful vision of the future. He suggests that as our understanding of the universe deepens, we will continue to uncover new insights into the nature of reality and our place within it. The universe, he argues, is not a cold, indifferent machine, but a dynamic, evolving entity in which life plays a fundamental role. Conclusion: The future of cosmology. In the conclusion of On the Origin of Time, Hertog reflects on the future of cosmology and the exciting new questions that lie ahead. He acknowledges that many of the ideas explored in the book, such as the quantum multiverse, the role of life in the universe, and the emergence of time are still speculative and remain on the cutting edge of scientific thought. However, he argues that these ideas represent the next frontier in our quest to understand the universe. Hertog emphasizes that cosmology is a field that is constantly evolving. As new discoveries are made and new theories are developed, our understanding of the universe will continue to deepen. He encourages readers to remain open to new ideas and to embrace the uncertainty that comes with exploring the unknown. The book closes with a call to action. Hertog urges readers to continue questioning the nature of reality and to remain curious about the mysteries of the cosmos. He reminds us that the universe is a vast and wondrous place, and that the journey to understand it is far from over. Hertog's message is one of hope and optimism. The future of cosmology is bright, and each new discovery brings us closer to answering some of the most profound questions about existence. The universe may be complex and mysterious, but it is also a place of beauty and wonder, filled with infinite possibilities waiting to be explored. Call to Action on the Origin of Time challenges readers to think deeply about the nature of reality, the role of life in the cosmos, and the mysteries of time and space. Hertog's exploration of these profound questions leaves us with much to ponder, but it also invites us to continue the journey of discovery. If this book has sparked your curiosity, there is much more to learn. Keep exploring, keep questioning, and never stop seeking to understand the universe and our place within it.